Good afternoon, everyone. I'm Yash Kumar, currently pursuing my Bachelor's of Computer Science in BITS Pilani, Goa. I'd like to thank the sponsors and the organizers of ICCAI 2022 for providing me with an opportunity to present my research paper titled Machine Learning Based Analysis to Identify Speech Features Relevant in Predicting Alzheimer's Disease. Alzheimer's disease accounts for 70% of all dementia worldwide. It is a progressive and irreversible neurodegenerative disease causing brain cells to die, thereby affecting mental faculties of a patient. While it has no ubiquitous definition, it is often associated with multiple symptoms. Speech deterioration, especially, is an important symptom when it comes to neurodegenerative diseases. Through this research, we propose a non-invasive method of predicting and distinguishing Alzheimer's from other neurodegenerative diseases by analyzing factors of speech of individuals facing neurodegenerative diseases. As of today, Alzheimer's has no cure. The existing treatments alleviate symptoms and delay its progression. Through this study, we aim to make the diagnosis of Alzheimer's easier and its early detection possible. The novelty that we have introduced in our work was the following: training and comparing performances of multi-class classifiers for distinguishing among probable AD, possible AD, MCI, which is mild cognitive impairment, memory impairments, vascular dementia, and control groups, and binary classifiers for distinguishing between probable AD and control. Performing a qualitative study on the impact of various speech features in predicting Alzheimer's and classifying it from other neurodegenerative diseases. Studies performed on the Dementia Bank dataset include that of Wonkerl and others, who employed an n-gram based model on pit corpus, and using an equal error rate classification threshold, we achieved an accuracy of 77.1%. Jancheva and others worked to predict MMSE scores based on linguistic features of AD and related dementia. They used a bivariate dynamic Bayes net to represent longitudinal progression of observed linguistic features and MMSE scores over time. Fraser and others performed the work on transcripts and acoustic labels of audio from Dementia Bank dataset and used logistic regression for classification and achieved an accuracy of 81.92%. One of the more recent works, we have Karleker and others, who used neural networks on the utterances of 4 speech tasks in pit corpus and obtained an accuracy of 91.1%. However, they broke the speech transcript into individual utterances and treated those utterances as individual samples. In this way, the model tends to lose the ability to check the thematic coherence of the speech. Another popular work is of Sheehan and others, which they trained an RNN and used area under ROC for evaluation. We also have Shen and others, which is one of the best works that is there, that is available on the research papers, which is an attention-based CNN and bidirectional GRU, and they achieve an accuracy of 97.42%. Apart from the work that has been done on Dementia Bank, more work has been done and are relatively primitive. For example, Bucks and others, who used linear discriminant analysis of spontaneous speech, achieved an accuracy of 87.5. Lin and others, who worked on DEMAT care dataset using spectrogram features and analyzing it using logistic regression. Thomas and others, who also used n-gram based techniques on the ACADI datasets to distinguish control patients from patients having dementia of Alzheimer's type, and achieve a score of 95%. All of this is done on speech. The methods we have used. For our work in this paper, we have used the Dementia Bank Spit Corpus dataset, which contains transcripts of conversations with many people, many of whom have had different forms of dementia. You can see the class-wise composition of this dataset. And we have chosen this dataset as a lot of work has already been done in the past, and multiple performance benchmarks were available for us for comparison. It is also one of the most widely used datasets in Alzheimer's related research. The dataset contains speech transcripts of patients coming from different parts of the world, having up to 6 relevant and different types of neurodegenerative diseases. To extract the specifics, we use the following commands in the CLAN software. Or index of productive syntax for syntactic complexity. Eval for word type ratios, grammatical analysis, count of utterances, and flucal for fluency and pauses. Following the pre-processing of data based on TSM coefficient being less than 0.8, we retained 50 features to work upon. We trained multiple classifiers as listed below to make the predictions and distinguish AD from other neurodegenerative diseases. Both binary and multi-class models were trained, with the former just distinguishing between probable Alzheimer's and control, whereas multi-class distinguishes among all 6 classes of these neurodegenerative diseases. The following models were trained and the hyperparameters have been mentioned here. Another model was trained, which is not mentioned in the table, which is the k nearest neighbors. For this, we took n, which is the nearest number of neighbors, equal to 10 as the default value, because grid search for KNN would not serve great purpose. Let's move on to the results. For each of the mentioned models, we have calculated and compared accuracy, weighted precision, weighted recall, and weighted F1 score. That is the weighted mean of class-wise measures according to the number of samples present. Taking weighted mean of these metrics helps us giving equal importance to each class, even for classes that have small samples when performing multi-class classification. Let's move on to model-wise analysis. Over here, we can see all the values that we have mentioned in the evaluation metrics plotted in the table. The inferences that we have is number one, in multi-class classification, some of the classes, for example, memory, vascular, and at times possible AD, were not predicted at all for the test. The most possible reason for this is that there is a presence of very few samples for some of the classes, as we have seen in table 1. A small sample size for any particular class causes the models to overfit, as it is unable to learn underlying patterns and thus fails to generalize on the real world data. Another notable observation from our results is that in all the multi-class classifiers that we have trained, a significant fraction of participants with MCI were being categorized as either probable AD or in control group. This seems to align with the idea that MCI, or mild cognitive impairment, can be viewed as an early stage of Alzheimer's. Research has also shown that individuals with MCI have a significantly increased risk of developing Alzheimer's compared to people with normal cognitive function. Participants with memory impairments were also categorized as probable Alzheimer's. This may be due to the fact that Alzheimer's also affects memory. However, since less data was available for this group, further evidence is required for this conclusion. Now we move on to feature analysis. We are looking at the graph for XGB, decision tree, and random forest classifiers for both binary and multi-class. The y-axis denotes how important a particular feature, and the x-axis denotes the 10 most important features in decreasing order. The higher the value of feature importance, the more important the feature is. The observations from the graphs in figure 2 suggest that present participle and third person present tense markers are the most relevant factors for all the models in both us in general. Here, present participle, or underscore PRESP, is the form of the verb that uses ing with the base of the word. Most of the time, it performs the function of an adjective, though at times it performs as a word or a verb or a subject in construction. It's important to know that this is not the same as a gerund, where the verb is serving as a noun. For example, he is coughing. Here, coughing is a present participle tense, but coughing exhausts him. Over here, coughing means that it is a gerund. The third person present tense marker, or underscore 3s, is a verb phrase exclusively characterized by the use of the s inflection on the third person singular present tense. For example, she cycles instead of she cycled or Donna cycled. Now, we can see how an Alzheimer's patient would use pronouns and continuous third person present tense markers in their speech. This also suggests that speech of patients with Alzheimer's consists of present participle excluding gerunds and includes the use of present tense markers with third person reference. Coming to the conclusion, an exhaustive comparative study between the performance of models was conducted by plotting confusion matrices and neural networks were found to perform the best in both types of classification tasks. In this paper, we have also managed to show that there is a strong correlation between the speech of a person and whether a person has Alzheimer's or not. This was established by the comprehensive feature analysis that was done, which allowed us to make reasonable inferences about the relevance of certain features in helping a model make predictions. In all, the features present participle and third person present tense markers are the most relevant features among all the features that are available in distinguishing Alzheimer's from other neurodegenerative diseases. The above results and inferences that we have found are of course subject to the dementia bank dataset. Coming to the limitations of this study, we have the feature importance limitations. First of all, we cannot plot the feature importance for all the classifiers. The reasons are that KNN does not provide a prediction for importance or coefficients of variables, since it gives equal importance to each of the neighboring data points. The FPC that we trained has used a RBF or radial basis function kernel. Since this kernel transforms the features and classification is done using the transformed features, the importance of coefficients cannot be traced back to the original features. And thirdly, a neural network, again, it is a non-linear model, and hence feature importance cannot be determined in terms of the original input features. Moreover, the data that is provided by the dementia bank dataset, while widely used, exhibits data deficiency for certain neurodegenerative classes. Results may be exclusive to this dataset, and transfer learning might not always be possible. Coming to the implications of this, extending this work on a larger and much more robust dataset in the future is something that we plan on doing, with which we can study biases and experiment more heavily in order to improve generalizability of the models. Development of artificial data via GANs or similar techniques might be a possible solution if enough data can be acquired. Encouraged by our findings, we hope that our work would serve as a good reference point for others who are aiming for the same research projects and aiming to make the diagnosis of Alzheimer's easier with early detection possible. Thank you, and I'll now entertain any questions.
Yes, can you hear me now?
Yes.
Oh, so
yes,
please stop sharing your PPT so that I can ask you some question. Yeah. So yes, the first question to you is Alzheimer. You have worked. So this is a project or something else, or just a paper you were doing?
So this is a paper that I did in fulfillment of one of my projects. This is a self-guided project that I did under the mentorship of one of my professors over here.
So I mean, you must have gone through with lots of papers, right? Yes.
I'm sorry.
So you must have gone through with lots of paper related to Alzheimer,
exactly.
right?
Exactly.
So what is the difference between Alzheimer and dementia? If I would like to ask you, so how you will explain that? What is dementia, and how you would like to apply those models on these things?
Okay. So there is, like I mentioned before, there is no ubiquitous definition for Alzheimer's or dementia. It is often associated with the symptoms that it has. For example, memory loss, language deterioration, mood changes, impaired judgment, and loss of initiative. However, when a person transcends from regular dementia to Alzheimer's, these conditions are vastly exaggerated. And Alzheimer's in itself does not really have a cure for this. So the early detection, the study that we have done helps in early detection of Alzheimer's and whether it can be prevented to a certain extent. Because preventive measures do exist, but there is no cure for Alzheimer's disease.
Okay. So how do you select the important variables while working on a data set? You have mentioned the different data sets you have worked on. So what are those parameters you have worked on? Basically, how do you select the important variables? That what to take, what not to take? Your guide has helped you in this, or you have done some self-work, something like that?
We went through the pre-processing of data. The three commands that we have used, which is epsin, eval, and flucalc, listed almost all the features that were annotated in the speech transcripts that were available to us on the dementia bank dataset. We extracted a total of 108 features, out of which we retained only 50. There are two ways we cleaned this data. One was using the Pearson coefficient, which is used in the correlation matrix, and any value that was greater than 0.8 in relation to each other was removed. This, you should say, relation was not exactly gradual, and we found that 0.8 was a good place to, take the Pearson coefficient limit. The second thing is we had to clean the data ourselves. There were a total of 1,200 participants that were available in this study. Some of them did not really have all the details, so we had to remove those details. And in terms of interrelations, there are some features which were too interrelated to just be included. For example, there is a feature known as MLU utterances, which is mean length of utterances. That in comparison with the number of words that are there in speech are more or less correlated, because the length of an utterance is very small compared to a length of a word. The utterance is something known as which an Alzheimer's patient would usually say, whereas a regular word is a regular word. So the length was highly correlated with the number of words that were available. So we removed one of those features. And obviously, Pearson coefficient had to play a big role in this.